All right, today we're going to wrap up these tests of convergence for numeric series. Now, the one we're going to start with is the ratio test. Now, we've already done the ratio test. I kind of explained it to you, but we did it in a way where we did the ratio test on a power series, which is series that had x's in them. Now, the ratio test works very similarly when it comes to numeric series, but basically what we get to do with this is when we go to run the ratio test, there's no x left behind, we just get a number. And if the number that we get is less than 1, then the series converges. It converges absolutely, which really means that whether it's positive or negative, it converges. We drop these absolute value bars on it, so that's why it says converges absolutely. So if the limit we get is less than 1, it converges. If the limit we get is greater than 1, it diverges. And if the limit we get equals 1, then the test is inconclusive, and that means we should have tried another test. Okay, so all we're going to do with this ratio test is say, all right, here's what we got. We want to run a ratio test on it. So if I take example 1 and I want to run the ratio test, we've already done ratio tests, so I'm just going to pick right back up where we left off. And I said, when you do a ratio test, really what you're doing, sorry, I don't know what just happened there. Really all you're going to do here is you're going to take the limit as n approaches infinity of a sub n plus 1, which is going to make this n plus 4 factorial divided by 3 factorial n plus 1 factorial and then 3 to the n plus 1 times a sub n flipped upside down. So remember that we had a sub n plus 1 divided by a sub n. It's like times the reciprocal of a sub n. So we have 3 factorial n factorial 3 to the n and then n plus 3 factorial. And then we basically want to know, what does this equal? Now, my favorite part about the ratio test is you get to cancel all kinds of stuff, and I always find that really, really fun. So we have n plus 4 factorial and n plus 3 factorial. So this basically just cancels with that guy's exclamation point. N factorial and n plus 1 factorial cancel with that guy's exclamation point. 3 to the n plus 1 and 3 to the n just basically leave a 3 on the bottom. 3 factorial and 3 factorial cancel out completely. So now I have the limit as n approaches infinity of, let's see, n plus 4 is the only thing we have left on top. And on the bottom we have an n plus 1 and a 3. And I want to know what that equals. Well, the degree of the numerator equals the degree of the denominator. And if I take the limit as n approaches infinity, I would have the ratio of their coefficients, which is technically a 1 and a 3. So this limit is 1/3. Then we come back up here. Is 1/3 less than 1? It is. Therefore, this series converges. Ta-da, done. On to the next one. So if I want to find the limit for this guy, I take the limit as n approaches infinity of a sub n plus 1. I don't know why those boxes show up. I apologize. And then 3 to the 2n plus 1 times a sub n flipped upside down. So that's 2 to the n over n times ln n. All right, now I want to know what this limit equals. So what can I cancel? Well, 2 to the n and 2 to the n plus 1, just leave a 2 behind. And yeah, that's pretty much it. So now I have the limit as n approaches infinity of n plus 1 ln n plus 1 divided by 2n ln n. Alright, what's that go to? Ooh, God, I don't know. Well, if I plug in infinity right now, I have infinity over infinity, which means I could do L'Hopital, but I really don't want to do L'Hopital because then I'd have a product rule, and I don't want to do that. So I'm actually going to use one of the limit laws. One of the limit laws says if you have a product like this, you can separate it into two limits. So I can take the limit as n approaches infinity of n plus 1 over 2n, and then multiply that by the limit as n approaches infinity of ln n plus 1 divided by ln n. I can totally do that if I want. Well, fantastic. That works for me. So then, let's see. The limit as n approaches infinity. Let me scroll down here. Of n plus 1 over 2n, this guy becomes 1/2 because of that whole degree rule. And then this guy over here becomes, well, infinity over infinity. So I'm going to just hop over to the side and do a L'Hopital. The derivative of the top would be 1 over n plus 1. The derivative of the bottom would be 1 over n. If I keep switch flip, this is like n over n plus 1. And as n goes to infinity, to this, I get 1. So 1/2 times 1 is 1/2. 1/2 is less than 1, so ta-da, this guy converges too. Fantastic. Alright, last but not least in the basic test here is the root test. Now, I gotta be honest with you, let's see, in all the tests I can remember, I have not seen the root test come up on an AP exam. It's in the curriculum, so it's totally fair game, but if your brain is so jam-packed that you're like, I can't do it anymore, I can't shove one more test inside here, then don't worry about it. Walk away, be happy, you're fine. But we have to do the root test, so I'm going to go through it as quickly as I can. The nice thing is it's really obvious when you're supposed to do the root test, because if you look at both of these examples down here, I've got something raised to the nth power or the n squared power. So honestly, the root test works out really, really well and very easily for stuff like this. But again, I don't think it's going to come up for you. So the root test basically says, assume you have one of these really funky looking series where you've got this whole bunch of nonsense raised to the n or raised to the 2n or something like that. What you basically do here is you take the limit as n approaches infinity of the nth root of the series itself. If that nth root converges to less than 1, then the whole thing converges. If the limit goes greater than 1, then it diverges. And if it equals 1, then you got to try something else. And usually what that means is if it equals 1, it means you kind of did the wrong test. You should try a different one. So if I take the nth root, so I take the limit as n approaches infinity of the nth root of 2n plus 3 over 3n plus 2 to the n, well, you know what? This kind of looks nasty, and a lot of people can't see the whole canceling idea here, so I don't usually rewrite it like this. I write it like this. Go away, taskbar. I write it like this. I say that really means that we have the limit. Okay, now what is going on, computer? Sorry, guys. We have the limit. There we go, that's better. As n approaches infinity of 2n plus 3 over 3n plus 2, all raised to the n, and then the nth root of that means I'm raising it to the 1 over n power, right? The third root is the 1/3 power. Square root is the 1/2 power. So the nth root is the 1 over n power. Well, what do you do with exponents being raised to each other? You multiply them, of course, because exponent laws are second only in my favoritism to log laws, because they're so incredibly related, but I digress. So n to the 1 over n, whoop, these guys cancel out. So now I have the limit as n approaches infinity of 2n plus 3 over 3n plus 2, which, let's see, 2n plus 3, 3n plus 2, same degree, ratio of the coefficients, 2/3, 2/3, less than 1, converges. So this big mess of nonsense is a series that converges. Ta-da! Alright, same thing over here. I got a whole bunch of stuff to the n squared. Well, that looks a little weird. Don't worry, it gets better. So I take the limit as n approaches infinity of the series I was given, raised to the 1 over n power. Well, what do I do with exponents when it's a power raised to a power? I multiply them, of course. So I take the limit as n approaches infinity. N squared times 1 over n becomes n of 1 plus 1 over n to the n. And that limit you all know is e, wait, come here, equals e. Since e is, no, it's not less than 1, e is greater than 1, so this diverges. Done. Okay, I know 99.9% of you going, whoa, 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 Mrs. Weber, 1 plus 1 over n to the n is e. You told us that we all know that. Well, it's because I told you already. Do you guys remember, way back when we did L'Hopital, case 4 of L'Hopital was that case where we had one that showed up and it was the limit as x approaches infinity of 1 plus 1 over x to the x. And when we went to evaluate this thing, I said you set it equal to L, and then you take the ln of both sides, and you evaluate the limit, and blah, 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 blah. This thing showed up, okay? This exact limit showed up, and the answer to that limit was E. Should you know that? Yes. This is one of those cases where you probably haven't memorized it because it hasn't come up before, and I totally understand that. But if you can find it in your brain somewhere, you should know the limit as n approaches infinity of 1 plus 1 over n to the n equals E. If you can't remember that, it's okay. The chances of you needing to know it for the AP exam are very, very small. But seeing as this is where E comes from and E is incredibly important, you should try to know it. Okay? Long story short for this problem, though, what you need to know is this limit does in fact equal E. Since E is bigger than 1, that means the series diverges. Alright, that's the end of our convergence test for positive term series. There's a lot of them, and there's a lot to figure out. Oh my god, which test do I use? Is it the integral test, the ratio test, the p-series test, the nth term test, the root test, I'm forgetting one. What am I forgetting? The limit test, the limit comparison test, the direct compare. Oh my god, there's so many I can't even remember them myself. Positive term series are a big pain in the neck. I will help you get through these. Don't panic. I have a nice little flow chart. We'll go through it. But long story short, there's a lot, and they pretty much stink. I'll make them easier, but they stink. Now, turn the page. Here's where your life gets easier. Not every test, not every series, pardon me, is a positive term series. Lots of series are alternating series. Alternating series are alternating when they have alternating positive and negative terms. So an example, and you don't have to write this down, but an example of an alternating series would be like 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, and so on. That's an alternating series. You can have alternating geometric series. You can have alternating any kind of series you want. If they go positive, negative, positive, negative, positive, negative, then they're alternating. Here's the awesome thing about alternating series. There is one test for alternating series. It's the alternating series test. If you know that you have an alternating series and it satisfies the two conditions below, then the series converges. First condition, if the limit as n approaches infinity of the absolute value of a sub n equals 0. Let's write this as an AKA. AKA, if the value of the terms decreases to 0. In other words, let's look at this one up here. 1 minus a half plus a third minus a fourth. Da, da, da. So if I look at just the value of the series and ignore the sign, 1, a half, a third, a fourth, a fifth, a sixth, a seventh, an eighth, a ninth, da, 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 are all those fractions headed towards 0? Yes. Yes, they are. Therefore, condition 1 met. Condition 2, a sub n is greater than or equal to a sub n plus 1 is greater than or equal to 0 for all n. You know what that means? It means that the terms always decrease. So I don't do something like 1 minus a half plus a third minus a fourth minus a sixth. Then I jump to like plus a fifth minus a fourth plus a third. As long as I don't wiggle wobble up and down in the fractions, as long as the fractions are headed towards 0 and they're strictly heading towards 0, they don't kind of go towards 0 and then come back and go and come back. If you just have fractions, they're alternating, they go to 0, it converges. End of a story. No other test. So let's look at this guy right here. I have this funky thing, negative 1 to the n. When you see negative 1 to the n, ding, 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 this is an alternating series. As soon as you know it alternates, all you have to do from there is basically ignore the fact that it alternates for a second. Look at this guy. 1 over ln n. As n gets bigger, does 1 over ln n go to 0? Well, yeah, because it goes to 1 over infinity. So since this limit goes to 0, the series converges. Done. End of story. No other test. Negative 2 to the n over n. All right, well, I'm not really convinced that this alternates, so I'm going to write out the terms. So if I write out the terms here, when n equals 1, this is going to be negative 2 over 1. When n equals 2, this is going to be a positive 4 over 2. When n equals 3, this is going to be, let's see, a negative 8 over 3. So this is negative 2 plus 2 minus, well, 3 and 8 is 2 and 2/3. Are these headed towards 0? Nope. Therefore, it diverges. End of story. It's an alternating series. It's not going to 0. It diverges. If it's alternating and it does go to 0, it converges. That's it. That's all you need to know. Okay. That means the alternating harmonic, the one that I wrote right up at the top, 1, a half, third, a fourth, a fifth, a sixth. When we had a regular harmonic, that diverged. But if you have an alternating harmonic, since it's actually an alternating series and the absolute value of the terms is approaching 0, the alternating harmonic converges. Oh, my pen died. There we go. Converges. Ta-da! Done. All right. Last but not least, another easy thing for alternating series is if you want to estimate the sum of an alternating series, piece of cake. The sum of a convergent alternating series lies between any two consecutive partial sums. Usually, how they test that on the AP, whoa, what just happened there? Who knows? Come back. Usually, when they test that on the AP, they want you to know the following. The error of a partial sum for an alternating series is less than the first omitted term. So basically, the first term you leave out, that's the most you can be off by. Now wait a minute, this AKA doesn't read anything like what I wrote above there. The sum of a convergent alternating series lies between any two consecutive partial sums. Well, think about that. Consecutive partial sums mean you just add on the next term. So if I lie between two partial sums, that means the next term I added on was too much. That's why the error is less than the first omitted term, because the first omitted term is trying to make the series better, but I kind of overcompensate by adding an extra term, and I kind of wiggle wobble back and forth. So here's one way that that can look. How many terms of the series are necessary to estimate the sum of this to with an error of 0.00005? Okay, well, all I would really need to know there is which term is just bigger than that. So I would basically want to know negative 1 to the n plus 1 over, what just happened? Ah! Sorry guys, computer's acting up there. There we go. Negative 1 to the n plus 1 over n plus 1 squared. I want to know when this is less than or equal to 0.00005. So we can just make this an equation. Now, when we talk about error, we usually want to talk about positive error. So what we do is just basically ignore the fact that this is a negative 1 to a power and just call it 1. 1 over x plus 1 squared equals 0.00005. And I'm just going to let my calculator tell me when that happens. So in y equals, let's see, yes, I have a fancy calculator on this computer now. So if I go into y equals 1 divided by x plus 1, oops, I forgot my parentheses, x plus 1 squared minus 0.00005. Now I want to see how many terms are needed. So when I go to my window, I'm going to set my x to 0, and since x represents n, and I want n to be the number of terms, I don't know, let's do like 25 terms. And then I just really want to know the y-intercept of this, so I'm going to go, let's see, from negative 0.00001 to positive 0.00001. Is that the right thing? Yeah, it's different, but negative to positive is fine. Now, why didn't I go negative 1 to 1? Because I'm dealing with a really tiny number right here. So I didn't think that that was going to be good enough. So I made my Ymin and Ymax go from a negative to a positive, but a very small negative and a very small positive. And I'm hoping I can see where this crosses the x-axis. Please, 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 please. Please show me. Where are you? Dang it, that didn't work. Let's see. Now, I gotta be honest, I don't have my answer key at home here, so I'm just gonna bump this up and say, you know what? Maybe this is bigger. So let's go out to 100. And I'm going to change this so that these are both 6s. Just because it's bothering me that they're uneven. There we go. Please work. Please work. I really want to show you this working. Darn it. You know why this isn't working? Because Mrs. Vibber's being silly. Let's think about this for a second. This is n plus 1 squared, right? I need 1 over n plus 1 squared to be 0.00005. How about I just stop being silly and stop relying on my calculator so much? 1 over x plus 1 squared equals 0.00005. Mrs. Vibber, duh. How about you just do this? X plus 1 squared equals 1 divided 0.00005. Come back here, calculator. Just do some math for me. Quit out of here. Come on. Seriously, quit out of here. 1 divided by 0.00005. Enter. What's that? 20,000? So x plus 1 squared equals 20,000. Square root that. I'm just going to raise it to the 0.5 power, which is the same as square rooting. 141. Take away 1. 140.4. So x is 140.4, which means we need 141 terms. Silly, Mrs. Vibber. You could have done that in a short way. Silly calculator. 141 terms. If you didn't really understand that, don't worry about it. I'll talk about it later when we see it in AP questions. I am going to sign off now because I've been talking for 22 minutes. I will see you guys tomorrow. I am sorry that I wasn't there. I had a house of sick. Enjoy your day, and we will see each other tomorrow.